Thank you very much. There we go. Yes, Cisco and Clepsydra have been working together also in an Horizon Europe project called Rebecca. And here we're going to present some of the results. The Rebecca is mainly to develop some European RISC-V chips. So we're going to show what we have been doing around this topic. So briefly, Clepsydra is a software company. We develop high-performance AI solutions for different edge devices. At the moment, mainly we're working in a space, different devices, mainly with Geisler and other providers. This is our main business. The core of Clepsydra is an algorithm called the event loop, which is kind of depicted in a very artistic manner here, but basically it's a log-free ring buffer with log-free memory management. It's extremely efficient. It's inspired from some of the techniques used in the financial trading industry, where I have a very strong background. It's been currently granted a patent. It was granted a patent last year, so we're very happy about this. And the algorithm is extremely efficient. So it requires, this morning we was mentioned about the atomic instructions and log-free instruction in the RISC-V. We heavily rely on those. So without this, we are nothing. Super briefly, Clepsydra, some of you may have seen this before. Clepsydra relies in a two-dimensional threading model to run AI. So we have two types of threads. Some of them we call the pipelining threads, which basically, this is the event loop. So we kind of split the model into different portions that are running different cores using the event loop. This is the first type of thread, and the second type of thread is the standard parallelization threads, so where we parallelize convolutional layers, etc. So different configuration of these allow different type of optimization. So relying heavily on pipelining allow us to get a very low power performance usage when we run AI, which is typically quite interesting for telecom applications in a space. On the other extreme, if we rely heavily on parallelization threads, we get a very low latency at the expense of a higher CPU usage. But it could be the typical use case of this is more like a rendezvous and planetary landing applications in a space. And somewhere there is a combination of parallelization and pipelining that give us the highest possible throughput. This is mainly interesting for Earth observation type of applications. But in order to find this, you need to use some certain type of tools that we provide also in Clepsydra in our software. So with that, I think we can move into the introduction to Cisco.
Yeah, thank you, Pablo. So Cisco is a European company that is providing a real-time operating system and hypervisor, which is unique on the market because he has two types of qualification. One for safety, according to avionics, but also railway and space standards, but also for cybersecurity with common criteria EL5+. So it's based on a microkernel, also with a strict spatial and time partitioning, which allows mixed criticality. And the hypervisor allow you to put other type of API on top of or on one. So you can run Linux on top of it, even Windows if you want, but I'm not sure in space it will be very helpful. We have also POSIX API and a rank 653, which is mainly used in the avionics market. Of course, we support multi-core processor with different type of architecture, including RISC-V. So yeah, the application we did with Clepsydra is based on PikeOS. So the first platform we were using is the one from Teledyne based on the ARM LX2160. So it's a high powerful ARM AS72 cores. On top of it, so as you can see with the diagram here, we implement different type of partitions. All of them are based on our own Linux distribution with real-time patches. And then you have the global stack that is provided by Clepsydra.
Mm-hmm. Yeah, so basically we deploy with Clepsydra 3 AI algorithms that are running in parallel. One is for asteroid landing. Basically, they detect. There should be a demo from Microchip showing this, trying to estimate the attitude of the asteroid at any given time, so you can prepare for landing. The other algorithm is a geolocalization for the moon. It's a very interesting model. So you're just looking at the picture of the moon from a satellite in the moon. You can determine the lat and long. And finally, another one from what Leonidas presented earlier, the OVP-Mark ML model, the ship detection to detect ships from space. It's not that you need to do all 3 things at the same time in a spacecraft. You're not landing an asteroid in the moon and detecting ships, but at least it shows that you can run multiple models in parallel in this processor with the support of our Clepsydra inference engine. No? Looking into the RISC-V of the Rebecca project, we have a Clepsydra. We develop our own benchmarking tool because we need to do a lot of benchmarking because our main business is to do high performance software. So we're constantly benchmarking with other tools, for example, TensorFlow Lite and other tools. What is very important is we always do like a layer breakdown. I mean, I don't know how familiar you with AI, but AI is a deep neural network is a group of different layers running in parallel or sequentially. This is where we do a breakdown to make sure that every layer is optimized efficiently. So this is a little bit how the tool looks like. You enter some information, the model, how many cores you want to use, parallel threads, execution, and then you get some results. But the important thing, let's go to the actual thing. Yes, we tested obviously with the OVP-Mark again, the models, ship detection, cloud detection, etc. So these are some of the performance results. This is in the Polar Fire. So this is from another project we are doing with ESA, where we're testing Clepsydra on the Polar Fire. We compare to TensorFlow Lite. As you can see, the performance of Clepsydra is massively better than TensorFlow Lite here. So in terms of the CPU consumption, we're talking about one fraction of the CPU that the TensorFlow Lite needs. And more importantly, and that's what made me extremely happy, is that the latency that we can achieve with Clepsydra is in the order of 1/5 of the latency that TensorFlow Lite can achieve on the RISC-V processors. It's extremely good result for us. It shows that the performance we can achieve with our software in the RISC-V is extremely good. By the way, we saw similar results on the Noir 5 as well from Geissler. So it's consistent results with this with the Noir 5 of Geissler. So this was very good results. So these models here are what we call the light models because they are kind of light in terms of the speed and processing power. But we also tested with some heavy processing layers here. As you can see, the CPU consumption is much higher, but the latency remains quite good now for Clepsydra. So in that sense, very consistent results. And then for the Rebecca project, we did a similar benchmarking on the Rebecca chip. The Rebecca chip is a RISC-V processor developed in Greece, if I'm not mistaken, with one of the consortium partners. And what we saw is that the latency, forget about the CPU because the CPU is not very good. Consumption of this Rebecca chip is still work in progress. But it was very interesting is that the latency was double the latency that we can achieve, that can be achieved with the Polar Fire. So this is kind of interesting for a brand new RISC-V implementation, fully made in Europe. It's not about results. Yeah, similar more results on the same area. And finally, yes, before we run out of time, I will give it back to Jean-Didier. Sorry.
Thank you. No problem. Yeah, the roadmap I would say is more to move to RISC-V architecture with the same demonstration, with the same framework, and the goal is to really use the hypervisor capacity of PikeOS. As you can see in the diagram here, we want to use our own APIs, the PikeOS one, also keeping some Linux partitions and also maybe having a POSIX partition so that people can easily install their own application with the standard API. So, yeah, with of course the protection between the partition, which is the heart of the PikeOS qualification we have.
So exactly. So this is where we're heading as well with Clepsydra. So we did a preliminary integration with Cisco using Docker. This is the setup we already have supported, and this is to move towards more native support of execution of model directly on the PyCOS. And for that, this is the roadmap of Clepsydra as well. This is where we're heading as well, with the support of Cisco. We already support several of these processors, but more in the Linux and Artem's operating system, but we're moving towards the certified version of PyCOS towards the same processors. Good, I think with that, we're done now. Thank you very much.
That's it, thank you.